Now what I want to do is expand the idea of working with gradients to 3 dimensions. A directional derivative in R3 space involves finding some slight. If I want to expand directional derivatives into 3D space, I need to make some slight adjustments to my thinking. The gradient is a vector in R3, which means that it has 3 components. The analog to a level curve in R2 is a level surface in R3. So a surface that's defined by W is equal to the function f of xyz will have level surfaces that are given by equations in the form f of xyz is equal to c, where c is some constant. These level surfaces make up layers that can create a full 4-dimensional surface that's similar to the idea of layers in an onion. If I'm given the function f of xyz and a unit vector given by u is equal to the components u sub 1, u sub 2, u sub 3, the directional derivative can now be written as du of f at ABC is equal to fx at ABC times u sub 1 plus fy at ABC times u sub 2 plus fz at ABC times u sub 3. The gradient of f at xyz is given by the vector with components the partial of f with respect to x, the partial of f with respect to y, and the partial of f with respect to z. This means that my directional derivative of f at ABC can also be written as the gradient of f at ABC dotted with the unit vector u. The actual rate of increase is given by the magnitude of the gradient of f at ABC, where the maximum increase will occur when the gradient of f and the unit vector u lie in the same direction. This will give me a maximum decrease in my directional derivative when the gradient of f and the unit vector u are in opposite directions, and the directional derivative at f of ABC will be equal to 0 when the gradient of f and the unit vector are orthogonal. So let's let f be a differentiable function at xyz, and the gradient of f at xyz is given by the vector with components fx at xyz, fy at xyz, and fz at xyz. I'm going to expand that into vector component notation. I get fx at xyz in the I hat direction, plus fy of xyz in the j hat direction, plus fz of xyz in the k hat direction. The directional derivative of f in the direction of the unit vector u specified by components u sub 1, u sub 2, and u sub 3 at the point ABC can be written as the directional derivative du of f of ABC is equal to the gradient of f evaluated at ABC dotted with the unit vector u. So let's work an example. If I'm given a function f of xyz is equal to xy plus yz plus xz plus 4, the point P with coordinates 2, negative 2, 1, and the unit vector u specified by components 0, negative 1 over square root of 2, and negative 1 over square root of 2, we want to use these to compute the gradient of f, evaluate the gradient at P, and find the unit vector and the rate of change of the function in the direction of maximum increase at P. And then we want to find the directional derivative at P in the direction of the given unit vector. We start by taking the partial derivatives of my function with respect to x, y, and z. fx is given by y plus z, fy is given by x plus z, and fz is given by y plus x. This means that my gradient of f at xyz is given by the component vector y plus z in the I hat direction, plus x plus z in the j hat direction, plus y plus x in the k-hat direction. My gradient of f evaluated at 2, negative 2, 1 becomes negative 2 plus 1 in the i-hat direction, plus 2 plus 1 in the j-hat direction, plus negative 2 plus 2 in the k-hat direction. This gives me a vector with components negative 1, 3, and 0. The magnitude of the gradient of f evaluated at 2, negative 2, 1 gives me the rate of change. This is the square root of 10. I can use this rate of change to compute the unit vector. My unit vector is given by vector components negative 1, 3, 0 divided by square root of 10. This gives me a directional derivative of f at 2, negative 2, 1, which is equal to the vector with components negative 1, 3, 0, dotted with the vector that has components 0, negative 1 over square root of 2, and negative 1 over square root of 2. This dot product gives me a value of negative 3 over square root of 2. Now we've found the gradient of f, we've evaluated it at p, we have found the unit vector and the rate of change of the function in the direction of maximum increase at p, and we found the directional derivative at p in the direction of the given unit vector. Now you get to try it. Pause the video, and given the function f of xyz is equal to the quantity x minus z over the quantity y minus z, and the point P with coordinates 3, 2, negative 1, and the unit vector u is equal to the vector with components 1/3, 2/3, and negative 1/3, compute the gradient of f and evaluate it at p, find the unit vector and the rate of change of the function in the direction of maximum increase at p, and find the directional derivative at p in the direction of the given unit vector. When you're ready, restart the video to check your understanding. So the first thing I need to do is take the partial derivatives with respect to x, y, and z of my given function. Fx is given by 1 over y minus z. I'm going to multiply the top and bottom of this one to give me the quantity y minus z over the quantity y minus z squared. Fy, using the quotient rule, gives me z minus x, gives me the quantity z minus x over the quantity y minus z squared, and fz gives me the quantity x minus y over the quantity y minus z squared. My gradient of f at xyz is therefore given by 1 over the quantity y minus z squared times the vector components y minus z in the i-hat direction plus z minus x in the j-hat direction plus x minus y in the k-hat direction. The gradient of f evaluated at the coordinates 3, 2, negative 1 gives me 1 over 3 squared times the vector components 3 in the i-hat direction minus 4 in the j-hat direction plus 1 in the k-hat direction. This gives me a vector with components 1/3, negative 4/9, and 1/9. This is my gradient of my function evaluated at 3, 2, negative 1. The magnitude of my gradient evaluated at 3, 2, and negative 1 gives me the square root of 26 over 9. This is the actual rate of increase. My unit vector is given by the vector components 3, negative 4, 1 divided by the square root of 26. My directional derivative du of f evaluated at 3, 2, negative 1 is given by the vector with components 1/3, negative 4/9, and 1/9, dotted with the vector with components 1/3, 2/3, and negative 1/3. This dot product reduces to negative 2/3. This is how the gradient works in 3 dimensions. Be sure and let me know if you have any questions.